In this presentation, I consider diffusion in ideal gas mixtures made up of three components, and I wish to demonstrate the possibility of uphill diffusion. The diffusion process is described by the Maxwell Stefan equations that were put forward by James Clerk Maxwell and Joseph Stefan in the 19th century. This presentation is an abridged version of a video talk titled Uphill Diffusion that can be viewed on my YouTube channel. We now consider diffusion in ternary gas mixtures, and the objective is to demonstrate the possibility of uphill diffusion in such systems. We begin by formulating the Maxwell Stefan equations to describe the diffusion in ternary gas mixtures. The force exerted per mole of species 1 is balanced by the friction species 1 experiences because of relative motion with respect to species 2 and relative motion with respect to species 3. Similarly, the force acting per mole of species 2 is balanced by the friction species 2 experiences in moving relative to species 1 and the friction it experiences with species 3 in view of the velocity differences between species 2 and species 3. In view of the Gibbs-Duhem constraint, only two of the driving forces are independent, and there are only two equations to consider. There are three independent Maxwell Stefan diffusibilities, D12, D13, and D23. These represent respectively the inverse of the drag between 1 and 2, inverse of the drag between 1 and 3, and inverse of the drag between 2 and 3. D21 equals D12 as a result of the Onsager reciprocal relations. In setting up these equations, we ignore three-body collisions. That is the assumption normally made in the development of the kinetic theory of gases. The Maxwell Stefan diffusibilities D12, D13, and D23 are all independent of composition for ideal gas mixtures, and these can be determined with very good accuracy using the kinetic gas theory. An important advantage of the use of the Maxwell Stefan formulation, say in comparison with the Onsager formulation, is that the diffusibilities D12, D13, and D23 are independent of the choice of the reference frame, because these diffusibilities are defined in terms of differences in the diffusion velocities, one with respect to 2, one with respect to 3, and 2 with respect to 3. The constraint imposed by the second law of thermodynamics demands that these Maxwell Stefan diffusibilities be positive definite. Solving the Maxwell Stefan equations to obtain the component fluxes in ideal gas mixtures is not a trivial exercise if the number of components is 3 or more. in 1976, in a paper published in AICHE Journal, Krishna and Standart presented an analytic solution to the Maxwell Stefan diffusion equations for n-component ideal gas mixtures. This paper has been the subject of many citations over the years, and I'm going to spend some time describing the essence of the matrix method of solution developed in this 1976 paper. The work was done at the University of Manchester in the Department of Chemical Engineering, and the Department of Chemical Engineering was housed in Jackson's building. The second author of this paper is George Lennell Standart, who was professor of chemical engineering, and he died prematurely in 1978, shortly after the publication of this paper. So let us examine how the analytic solution to the Maxwell Stefan equations were set up by Krishna and Standart. To solve practical problems of relevance to chemistry and chemical engineering, we first need to recast the Maxwell Stefan diffusion equations in terms of the component fluxes. I demonstrate that for a ternary gas mixture. These are the set of two independent Maxwell Stefan equations. Because of the Gibbs-Duhem constraint, we have only two independent driving forces for diffusion, which are the chemical potential gradients for components 1 and 2. For ideal gas mixtures, the chemical potential gradients can be replaced by the gradients in partial pressures, or equivalently the gradients in the mole fractions of components 1 and 2, where Y1 and Y2 are the mole fractions of components 1 and 2. Let us define the molar volume. V sub m is R, the gas constant, times T, the temperature, divided by the total pressure. That is the molar volume. It is also the inverse of the molar concentration Ct, but Ct is the total pressure divided by RT. The fluxes of each of the components in a laboratory fixed reference frame is the total molar concentration times the mole fraction of that component times the velocity of transport u sub I. The total flux of the mixture n sub t is the sum over the three species of the fluxes Ni. The Maxwell Stefan equations can be rewritten in terms of the fluxes N1, N2, and N3 by introducing these relations for the component fluxes. Ni is Ct times Yi times Ui. It is important to note from the start that we have two differential equations for the two independent mole fraction gradients, and we have three unknown fluxes to determine. The Maxwell Stefan diffusivity is D12, D13, D23 can be determined from the kinetic gas theory, and the Onsager reciprocal relations demands that D12 equals D21. So let's first address the problem of determinancy, because we have three unknown fluxes and two independent differential equations. We need a third relation to bootstrap the problem. I restrict myself to steady state transfers, and under steady state conditions, the fluxes N1, N2, and N3 are Z invariant, and there are three unknown fluxes and a set of two independent differential equations subject to the boundary conditions. Z is 0, Y is Y sub 0. This is a column matrix of mole fractions. At Z is Z delta, Y equals Y sub delta, which are the mole fractions at the position Z is delta. We need an additional relation to make the system determinate. And in practice, this could be the constraint of equimolar diffusion, which translates to the requirement that the sum of the fluxes is 0. We could have a scenario in which one of the components does not transfer. We have Stefan diffusion. This could be because the components, say, get absorbed into a solution in which component 3 is insoluble, and therefore we have the situation of Stefan diffusion. Distillation operations, the fluxes times the molar latent heat of vaporizations, lambda 1 N1 plus lambda 2 N2 plus lambda 3 N3 is 0 because of the constraints imposed by the enthalpy balance. For gaseous diffusion with heterogeneous chemical reactions, the flux ratios are related to the reaction stoichiometry. So the first thing we acknowledge is that we need to invoke a bootstrap relation in order to solve the Maxwell Stefan diffusion equations. These bootstrap relations are dependent on the particular practical problem we are addressing. I illustrate the bootstrapping of the Maxwell Stefan diffusion equations by considering the experiments of Cartier and Schroth, published in 1975. A long narrow tube was taken by Cartier and Schroth and partly filled with a liquid mixture of acetone and methanol maintained at a temperature of 328.5 degree Kelvin. The total pressure was maintained at 99.4 kilopascals. Air flows across the tube and acetone and methanol will undergo vaporization, and the vapors will traverse the length of the tube, and we have in this open region we have ternary diffusion of a mixture of acetone component 1, methanol component 2, and air component 3. At the top of the tube, we have practically no acetone and methanol, and it's the mole fraction of air is taken to be unity. The compositions of acetone and methanol in the vapor phase in this portion of the tube was measured experimentally and plotted here by these symbols. Red circles are the compositions of acetone. It decreases to 0 at the top of the tube. This is the length along the tube. From here, Z is 0 to Z is delta. This is the dimensionless distance eta equals Z divided by delta. The blue triangles are the mole fractions of methanol in the vapor phase, which decreases from about 0.5 to about 0 at the top. The green squares are the mole fractions of air in the tube, which is determined by subtracting from unity the mole fractions of acetone and methanol. The example here being considered is one in which we have diffusion of acetone and methanol in air, which is stagnant because air cannot diffuse into the liquid mixture, or the solubility is nigh 0. So here we have an example of Stefan diffusion with the bootstrap relation. N sub 3 is 0, where 3 is the species air, which is considered to be a mixture of nitrogen and oxygen. The Maxwell Stefan equations may be solved analytically using this Krishna and Standart matrix procedure described in detail in my papers listed here. 3 papers are listed here, and the analytic solution is shown by the continuous solid lines. The agreement with the experimental data is indeed very good. The main message that I wish to convey is that the Maxwell Stefan diffusion equations to determine the fluxes require the specification of an additional bootstrap relation that is determinable from the particular situation or problem in hand. In this case, air is insoluble in the liquid mixture, and therefore its flux is 0, and we have an example of Stefan diffusion. Other examples, such as those for equimolar diffusion, have been considered in other video presentations that may be viewed on my YouTube channel. Consider the 2-bulb diffusion experiments reported by Duncan and Tour in 1962. Bulb A is filled with a mixture of nitrogen and CO2, 50-50. Bulb B is filled initially with a mixture of hydrogen and nitrogen in proportion 50-50. And the connecting tube between the 2 bulbs is initially closed, and the valve is opened at time t is 0. The 2 bulbs are now allowed to interdiffuse, and the compositions in bulb A and bulb B are monitored as a function of time. Plotted in composition space, we see that the compositions do not equilibrate in a linear manner. Rather, the equilibration trajectory is serpentine. A serpentine equilibration trajectory is a signature of uphill diffusion, as I have explained in my video presentation on uphill diffusion that may be viewed on my YouTube channel. The point I wish to emphasize here is that in order to solve the Maxwell Stefan equations for the three fluxes of nitrogen, carbon dioxide, and hydrogen, we need an additional bootstrap relation. In this case, since the components of the mixture cannot travel out of the system, in other words, cannot cross the boundaries of these bulbs, from a momentum balance, we note that the mass average velocity of the mixture is zero at the surfaces of the tubes. This implies that the condition of equimolar diffusion is valid, and that is the bootstrap relation that needs to be applied in order to solve the Maxwell Stefan diffusion equation. Indeed, the solutions of the Maxwell Stefan equations using the Krishna Standart matrix procedure is indicated by the continuous green and red lines. These solutions invoke the equimolar diffusion constraint imposed by the momentum balance.